Data flow. So I guess a question in the room is, what is data flow? Is that what people have come to ask about? Actually, who knows what data flow is? One or two only. Yeah, okay. Ah. So the response there is, I think I know. Yeah. It's, actually, just let me go back a slide. Data flow, the concurrency parallelism architecture. So actually, just before we deal with data flow, we perhaps ought to deal with the terms concurrency and parallelism. I've put up a couple of sentences here that try and capture the essence of these two words, because the meaning in computing is almost, but not quite, totally different to the English language. So these have to be treated as jargon terms in computing. So concurrency is really about your structuring your code, structure of your solution to the code, whereas parallelism, if it doesn't go faster, you have failed. There is no other reason for being involved with parallelism other than getting things to go faster. So here we are, the sentence that describes data flow. For once, I will actually read out a slide. An architecture comprising channels allowing data to flow from one operator to another, where each operator has multiple input channels, multiple output channels, and executes code only in response to the arrival of data on the inputs. Now, what's the sort of historical background to this model? And it's hardware. Okay, data flow computers, late 70s, early 80s, trying to get away from the hassles of the Turing machine, the hassles of everything that IBM was throwing at us in the way of processors. Manchester, yet again, doing a great job of researching into unusual ways of doing computing. And so, hence the term operator. It really was plus, minus, times was the operator that they were talking about in the hardware world. And it really was values passing from one operator to another. They were moving data around, not leaving it in memory. I've put a reference to one paper up there. There are a number of papers. That's just one that's easily accessible. The full PDF is online if you want to have a look at it. But data flow hardware didn't actually take off. There were one or two problems, and also Intel didn't like it because they wanted to sell chips, 8080s and things like that. So there wasn't a pressure to go with this rather bizarre form of hardware architecture because we weren't used to it. But the data flow idea, and I've just drawn a random picture there that's not entirely on the screen. Sorry about that. Blobs and arrows. Anybody recognise the blobs and arrows? Put a name to what they are. Yeah, all of those are actually true. But data flow diagrams. DFDs, absolutely. It's been around since the late 70s. And I've put there the classic book from Tom DeMarco, which introduces a data flow analysis. So information systems people have been doing data flow for 40 years. It's nothing new. At a very high level, not the hardware level, very high level. So we're looking at this diagram, and now we have got the whole of it in, and we're thinking, okay, well, what are these? Well, they're data flows, data moving from one place to another, data flows. And these, they call them operations if you want, you give them any label, you know. It's an activity that transforms one value into another value. Or in this particular case, we're transforming one value into 3 values going that way. We've got one here, 2 coming in, 2 going out. So I say multiple inputs coming in, multiple outputs going out. And you might think, given the highly functional nature of yesterday, that are these operators just functions? Operating, okay, admittedly they're producing multiple values, but we can always deliver a single value by delivering a tuple or something like that. So the idea of being able, a function, mathematical function being able to deliver multiple values is actually relatively straightforward. But no, these operators are not pure functions. You can have state inside them if you want. You can have side effects. If you want to do any input-output at all, you've got to have some form of side effect. Hence, in functional languages, you monads, etc., etc., etc. So going back to that definition, multiple inputs to an operator, the operator only executes code in response to the arrival of data on the inputs. So therefore, Dataflow is an event-based system because there is no main thread that computes. Each of the operators does something only when data arrives. So the synchronization is actually implicit in the whole model. We want to bear that one in mind. It's going to be very useful. Another word that's trendy around now is reactive. And so, Dataflow may be 40-odd years old, but it's really trendy because it's a reactive system. Okay, some of people are awake. That's good. Dataflow is not the only really ancient idea that's currently trendy. Actors, CSP, all these ideas from the 60s coming back as modern because we've suddenly discovered that shared memory multi-threading is a crock of effluent. And the purpose of these models is to get us out of that pit of excrement. We don't want to be debugging threads. Yeah, okay. How many people manage the heap when you're working with Java? 1 or 2? I bet you're doing sort of hard real-time type things with Java, or something like soft real-time, something like that? Kind of. Okay. No one else even glimmered. You don't deal with the heap. You say, oh, G1, just get on and deal with it. Oh, if you're not using G1, you're doing it wrong. So even if you're having to suffer with Java 7, get G1 onto the scene. Okay, how many people manage the stack in their computing? So why the hell are you managing your threads? They're just a resource. That's what fork join is about. So if anybody's using synchronized, you're doing it wrong. If I see the keyword synchronized in a piece of code, RM star is probably the most likely thing that you should be doing with it. That's what all this reactive systems, event-driven stuff is all about. Get the synchronization implicit in the model so that you do not manage the threads. The threads are a resource underneath which are self-managing. Just use the thread pools. Moreover, if you are doing shared memory, you're clearly doing it wrong. You should not be sharing memory at all. You should be passing messages from one single-threaded computation to another single-threaded computation. That's what actors are about. That's what Dataflow is about. That's what CSP is about. And we know that CSP is good because Google tell us so. It's the way that Go works. A lesson worth learning. It may be a 1974 technique, but it's very much a technique of today. So here we are with our channels and operators. We have a Dataflow network. We're moving information from one place to another. Each of those operators we expect to be single-threaded and not exchanging data in any other way than down the channels. That's the model we're going to be working with. So data flow systems are message passing systems, and each operator, okay, I say must, should. There are occasions when you want to do silly things with threads, but it's immediate yellow flag, be very, very careful. So under normal circumstances, each operator single-threaded. So are there any frameworks out there already doing data flow? Well, if you go to Scala, they'll say, oh yeah, we do data flow, and then they'll point you at Akka, which is not an unreasonable thing to do, and you find the keyword data flow and data flow variables in the Akka library, and then you discover it's all deprecated, which seems a bit sad, because data flow is a good idea and actually has nothing to do with web servers and event loops and all that sort of stuff that async seems to be aimed at through the Play framework. I'm sure good stuff's going to happen, but I think they've missed a trick. They don't have a proper data flow framework as far as I can tell. I may just have missed it, of course, so I await to be informed. Java, as we know, there is no existence of Java before March the 17th, 2014. So if you are actually using a version of Java that comes from before that date, stop it and upgrade to Java 8 immediately. But even so, Java before proper Java had futures, had fork join framework, had thread pools, all the good stuff that we needed, but didn't really have enough to get the abstraction level high enough to be really good for applications programming. You were still dealing more in the systems level. So if you're using maps and stuff like that and you're not using concurrent hash map, you're doing it wrong. And things like that. You've got to raise the level of abstraction. And completable future is the addition that is really, really interesting in Java 8 for doing all of this stuff. They've called it completable future. Most of the people, I think, would probably call it a promise. But then you get into weird and wonderful discussion of what's the difference between a future and a promise and stuff like that. And basically, they are roughly the same thing. For the purposes of this session, let's treat them as the same thing, future and promise. But completable future comes with lots of extra goodies, which make it well worth having. So just sum up that little bit. The frameworks that are out there claiming to be data flow have these single assignment thread-safe variables, data flow variables. It is one form of data flow. It is an interesting form of data flow, but it's not the full-on data flow. They're not channels down which you can send streams of data. It's just a one value that's being created there. So we want to go further than that Akka or async and completable future offer us. And so therefore we're going to have to be groovy. And I'm sure Jez was expecting me to say groovy at some point in this talk. Was that true? A question here?
Yeah, you're moving on to Groovy.
Yeah.
Do you consider RX Java, RX Scala?
Sort of, yes. I didn't have time to create any examples from those languages for this talk, so I thought I'd try and ignore them and hope nobody asked. I am informed. I have learnt something today. Excellent. I should have put RX Java and RX Scala into the talk. On the other hand, I'm actually irresponsible for GPars. And so therefore, I'm biased. So we are going to get Groovy in there somehow. So GPars is a sort of added extra It comes with Groovy distribution automatically. And it provides a set of abstract tools over the top of fork join, over the top of a CSP framework, and gives us, for the purpose of this talk, serious data flow. Over on this side, we've got the same sort of thing that you can get from Akka and Java. Almost over on this side, it says has data flow queue and so creates real data flow networks. This is the bit that I would claim is ultimately interesting, because it's all about flows of data, not one data item. Devoxx has this little thing, one does like to code, but it's not the complete statement. There should have been a doesn't one on the end. The full sentence, one does like to code, doesn't one, which is the ultimate expression of Britishness, that you've got positive and negative in the same sentence, affirming the brilliance of doing something. Haha. Okay, so I've been waffling for a while, and it's basically just introducing some of the ideas and concepts, because at the end of the day, this only makes sense if we've got some code to play with, some examples to have a look at. So I thought, what out of the infinite possibilities of problems can we do? Well, I tend to do sums. Normally I calculate pi. I've been calculating pi for about 7 years in a number of different ways. But I thought I'll be different in this session, and I'll just do some sums. So I thought mean and standard deviation. The background of this is I'm doing some micro-benchmarking, sort of JMH type things, but also micro-benchmarking with the D language. And so means and standard deviation is sort of hot topic for me just at the minute. But they're also really easy things to do. I mean, we use the term mean here not to be nasty and grumpy and stuff, but basically X bar. Some of the items divided by the number of them. And this is an embarrassingly parallel problem, a data parallel problem. We can partition sums into partial sums and scatter them across large number of computers. So easy access to parallelism. And if you've got like 10 items, you don't care. If you're trying to take the mean of 200 or 300 million items, you perhaps do care about employing the parallelism in your phones. Because remember, your phone is probably way more powerful than a Cray one ever was. So why we just use them for looking at cat pictures, I have no idea. Never mind. Unfortunately, the equation for standard deviation has fallen off the end there a little bit. So there should be, over here, a sort of closed bracket squared in there. So you're summing xi minus x bar, so the mean, and squaring it. And that means that you have to calculate the mean before you can calculate the standard deviation, which is a bit annoying. Okay, so we can do some data parallelism here, and we can certainly do some data parallelism here, but we can't actually calculate anything about this at the same time that we're calculating something about that. So for the purpose of this session, we've got two sorts of parallelism that we're looking at here, trying to compute as much as possible at the same time. So as a standard trick for the standard deviation, you recast it slightly in this form, and again, there's a sort of extra X bar close parenthesis. Oh, I've even done it wrong. I should have drawn a line here of where the failure is. So that last expression should have been minus n x bar, and a huge, great close parenthesis. And what this means is that the sum here is independent of x bar, which means that we can calculate that sum and that sum at the same time. Aha, good stuff. Not too mathematical for 9 o'clock on a Friday, I hope. Sure, for most people it's probably O-level-ish maths. Yeah. Have to think of some more stand-up jokes. So, what we want is code. And the slide template, which we were unveiled to use, tells us to put code examples on slides. This is boring. Therefore, we will immediately switch to IDEs, where we can do interesting things. And I will have to switch glasses so that I can actually see what's on the screen here. Okay, so you want to do things sequentially, and you probably want to do them in Java. Yeah? So we, I don't want to go too far that way. How's that font size doing for people? Down, right, okay, bigger. Yeah, cool. So I'll drag this down a bit. I'm not dragging down the level of the talk by any means. Okay, is that okay for people? Yeah. So what have we got here? Well, proper Java. So we got some array list that we are putting lots and lots of numbers into. And we're returning multiple values here. Rather than returning mean, standard deviation as separate computations, I'm wanting to do them all at the same time. So I've got a function here that's going to return the mean, standard deviation, and the degrees of freedom for the standard deviation all at the same time as a triple. But Java is completely inadequate when it comes to tuples. So we have to ship lists back, which is exceedingly dangerous. Which is very topical, the Dangerous Brothers. Okay, the black humour doesn't work. Never mind. Too soon. Okay. Rick Mayer would never have said that. He'd have just gone for the joke. Anyway, so we're returning arrays as list, which is dangerous. When what we really want to return is a triple. And we're doing lots of things with nans, nothing to do with bread. This is not a number. So I've been stalling a bit whilst people have been reading the code a little bit, so that we've got some context on which to work. So this version of mean and standard deviation is just providing us an overload so that we can do things with iterables. Java is inadequate in its use of iterables because it doesn't define anything useful on them. You actually have to have a collection before you can do anything useful, which is not going to be too good if you've got an infinite stream of data coming in from somewhere. You have to create a collection in order to do some streams with it. Okay, so there's a problem there. I'm sure we'll have to write in a bug report. This function here, working with a collection, so we can take the size of it. And if we've got no data, we're just returning, you can't calculate with no data. Go away, give us a problem we can do something with. If you've got one item in there, mean and standard, well, mean's easy. Standard deviation, again, is a bit of a problem because you actually need 2 or more items to have a standard deviation. And then the bit down here does all the interesting hard work for a real data set. So we'll switch into streams. You know you want to work with Java 8, don't you? So we switch to streams. We map to doubles. Something that perhaps didn't come out yesterday with all the maps and filters and things with the streams protocol is that they're all working with objects. And Most of the time, if you're doing parallel stuff, you want it to go fast. Working with objects doesn't go fast. You want to work with ints and doubles. And so we're specifically here mapping from a stream of objects to a stream of doubles. And for various sensible reasons, you have to do that explicitly. And all, in fact, we're doing in this particular first one for the summing of the xi, we're just converting the object value into a double value. So the map is there just to feed in a stream of doubles to the reduction operation, the terminal operation, which is sum. A beautifully named operation. It does what it says on the can. It does sums. For the sums of squares, the sigma xi squared, our map function just squares things up. Sounds good to me. And then we return the triple. So here's our mean. Standard deviation, so we do the squirt. Here's the minus n x bar, and various divisions. So far, so good. So far, so sequential. One of the issues was, can we do this in parallel? Of course we can. So we do it in, whoops, I need to press that button first. And then we need to do something like that. Okay, you have 3 seconds to spot the difference. Okay, time's up. What's the difference? Yeah, absolutely. We could have done it even easier, I guess. But there we go. You just parallel stream, and what you get is the use of every single call that's available to that JVM, the fork join framework underneath. You don't have to worry about the threads. Just gets on with it. This has almost, but not quite, nothing to do with Dataflow. This is the data parallelism side of things. And Java 8 gives it you for free. What about Dataflow? Well, Java, we have completable futures. So here we are doing mean and standard deviations over iterables. So I'm making things a bit hard for myself by not using a collection. But I'm leading up to trying to deal entirely with streams so that we can connect to a file that is just an infinite stream of data. That's where we're heading. So I've got myself here a completable future. And notice the static function there, supply async. You need the font a little bit bigger. Whoops. Yeah, it's me panicking about it falling off the edge over there. Oh, it just made it. Not quite. I suppose what I could do is that. Not easily. Has that dealt with the size issue? Yeah. I'll say the background issue is probably going to be too difficult to handle in a couple of seconds. Sorry? Let's not worry too much. We need the line numbers. Okay, so we are dealing here with an iterable, which means we don't have any of the really useful functions like size. So we're actually going to have to iterate over stuff. So we get these horrible imperative things going on here. And you do find you have to do that when you're infinite streams. Unless you're using Scala when they hide it all. I may or may not be able to show the Scala version. We need to get to the Groovy version fairly soon. But the critical thing is here, we've got abstractions here which say, here is a lambda expression, go away and execute it, and return a future immediately so that you can carry on. And when I need the result, I'll ask for it. So the count is a completable future of integer, and at some point we will be forced to know its value. But for the moment, we don't care. And then we create sum squares, sum and sum squares, all completable futures. And the java.util.concurrent, sorry, I should have edited that out, is a feature of this IDE being overly interested in doing everything for you. Oh, never mind. I'll rant about that later. And the rest of it looks fairly similar. We have data, we get an iterator, we get the next. That gives us the first item. Horrible way of doing head, but there we go. And the final expression looks exactly the same as it did before. Is this data flow? Yes. Have we got a synchronize in there? We haven't used the synchronize keyword, but we do have synchronization in there. Where is the synchronization? It's where these joins are. This is not thread join. This is, I need the data now. You could use get, but get has this interesting habit of having all these exception types that you're not allowed to ignore. Don't you just hate checked exceptions in Java? Yes. So therefore, they very cleverly provided the join method for all those people who like doing real work instead of try-catch blocks. And it just throws a runtime exception instead of all these checked exceptions, which is by far the best thing to do. So join could be taken as a thread type operation. It isn't. Well, it is under the covers, but we're not worried. It's I want the data now. I must have the value. I cannot continue without it. There's the synchronization point. It's an inherent part of the model, not something we have to go synchronize, protect against threads. No, we're data focused. All we care about is our data. Threads are infrastructure for someone else to worry about. So let's see how you might do this in a more groovy way. This expression is going to get ridiculously long, of course, isn't it? Oh, that was silly. Yeah, we only need to go to there. Okay, so we're now in Groovy land. So iterable has some interesting extras because how many times did you want to add new methods to the string class and couldn't? How many times did you want to add methods to number and can't because somebody in Sun, now Oracle, or OpenJDK, or some quasi-fascist organization like that, has said, final. This class is final. You are not good enough to be able to deal with this.
How many times have you wanted to punch a monkey patcher in the face?
The comment there is, how many times did you want to punch a monkey patcher in the face? Well, not often, because in Groovy and Python, you do monkey patching an awful lot. It's called mocks and tests and stuff like that. But what Groovy does do is have extension methods so that you can add new methods to any class at all. And this is wonderful, particularly with iterable. So we can, in Groovy, we can do interesting things over iterable. And in particular, one of my pet peeves is that Groovy chose the Smalltalk nomenclature here. So instead of having map and filter, it's got inject and collect, which, oh well, you just get used to it. So data.inject is actually a reduce operation. So we've got the initial value, which is a list triple, and at each stage we're computing a new triple. So exactly as people were saying yesterday with streams, you have to stream over items of the same type. And so we're injecting over a list of 3 items. So we're actually calculating the sum and sum of squares in 1 loop instead of 2 loops. Does it matter? Well, possibly not, but it's sort of interesting. Oh, clearly not. We could do it as 2 if you want anyway. But what's happening down here is exactly the same thing as was happening in Java. Groovy and Java are very related. It's just Groovy's better. How do we know it's better? Well, you think Groovy is a dynamic language. No, it isn't. Groovy is a fully compiled, statically typed language. Look, I'm saying so. At compile static tells you that the mean standard dev function is fully type checked at compile time and compiled out to byte codes. None of this namby-pamby dynamic stuff. No, that approach didn't work either. Never mind. But we're still returning lists, and I'm not too keen on that one, but what the heck, it works. But we still haven't really got much data flow in here, have we? No. So let's do some proper data flow. That's just data parallelism going on. So let's get some serious data flow going on. Whoops. I need the control. There we go. So we have channels. None of this single assignment variable stuff. We've got proper queues here. All beautifully thread safe, so that nothing can go wrong when working on the fork join framework. But that's the GPars people's problem, not GPars users' problem. So I'm creating the Dataflow broadcast is a distributor. So you remember in the diagram, you can a node can have multiple outputs. Here, what I'm doing is taking one input stream and splitting it into 3, so that the same value goes down all 3 of them. And then we've got some more well, these are just Dataflow variables, just to show we can do it. So this is the direct analog of the Java code. And so a task is an operator in the Dataflow technology. It's just that Václav chose the term task here rather than operator. And count arrow arrow n, yes, that's something else that Groovy can do that Java issued in 1992, was the ability for user-defined operators. So in Java, you're not allowed to have proper domain-specific languages. You can't do things like count less than n unless you're actually doing shift left. We're saying, oh, n is now inserted into the Dataflow variable count. So that's, if you like, the single assignment going on. And sum, arrow, arrow, total. The task is basically a function. The open curly brackets is a block of code that's being submitted into that function that then gets started in a fork join thread. So the task, that's spawned off 3 operators in our Dataflow network, and they're all immediate started. So they're all computing in parallel. And then we'll calculate the mean, and now we start injecting information into that first stream. So we set up the operators, connected them with Dataflow variables, and then pumped data into the first stream. So here we are, sticking data into the stream. How do we know when we've finished? We have to send a value in that says, okay, that's the end of the input stream. So I'm just using double nan here as a little marker of type double that's not a number, so it makes it a really useful end of stream value. So it's a trick, but it's a nice one. And so the operators know that when they see nan, they've got to finish their comma fairly quickly. No, it must. These jokes only work on a Friday evening, don't they? After a beer. And so that's why we've been asking, are we not nan? Because nan is being used as the terminate the input sequence value. But this is just really one Dataflow variable being set. We're still only able to do a stream of values and issue a result. Works fine. A lot of people want to do that. But the killer blow, if you like, is I want to do continuous calculation. I don't want to just take a stream of data and calculate one number. What I want to do is running mean, running standard deviation. So I'm continuously calculating numbers as a stream of data comes in. If you like, this is an analog for dealing with the Blomberg or Reuters feed, where what you actually want to do is to put the feed into some network, neural net or something, and out comes the instruction, buy IBM or sell IBM or whatever. So that's the analog you're wanting to deal with here. And the use of these Dataflow variables isn't going to cut it because they're single assignment. And so we've now got ourselves a problem where those channels must be sequences. They can't be a single value. And so what we've got here is, if you like, the full Monty of a Dataflow computation. And of course, you're thinking of all this code for a very simple sequential operation that we started with. Yes, so there is an element of this problem is, am I undermining the message? Well, I think not, because take this into a real-world problem, and I think you'll find the Dataflow is going to naturally fall out as the solution. Anybody involved in big data computations? One or two? If you're doing big data and you're doing SQL queries, you're doing it wrong. Because what you do is you dump out your 200 terabyte database and you feed it in as a stream to a Dataflow network and calculate results that way, do your queries that way. And people in the US have found that queries that they used to do with SQL that took about 3 weeks to give them a value, they can now do it in like 3 hours with Dataflow networks on a 16-core Sun machine. So it's proving itself. So if you're doing any sort of data analysis of sequences, you will want this approach. So what have we got ourselves here? We have got some queues. So here are our channels that I've been talking about in that diagram. I've got a splitter here, just a different technique for taking one stream and generating 3 streams with exactly the same data on. I've now got the channels between the count operator and the result operators, the sum operator, the sum squared operator. I've got myself actual operators, and my operators have input channels and output channels. I can create state within. So as I said earlier, these operators are not pure functions unless you want them to be. In this particular case, I have to have some state because I'm summing and sum squaring. And then I have the act of putting things on the output. So this operator does nothing until data arrives on the input. It then computes, puts some data out on the output, and then waits for new input. So it's very easily written. There's not a lot of code in there for each of these operators. So here we are, we're just summing some values to create the count, summing the xi to create the sum. Whoops, oh, that's because I didn't do that. I've gone too far. So there we're summing the squares. Trivial little expressions, single-threaded, but not pure functions. And now this operator has got 3 inputs, and the default is you have to have input on, you have to have values on all your inputs before you trigger. You can change that. You can put patterns onto these, but the default is you have input on all of these, and only then you trigger a computation. So we have got values from count, sum, sum square, and we're using what is effectively a lambda expression, a closure, to give names to those values. So this closure will be called once there is a value at the end, on the end of each of these channels, and this, and this will be the references to those values that arrived. Here we are pumping values in, and this could be an infinite sequence, a truly infinite sequence. You can just connect it to a sequence of values coming in from the outside universe. And at no point have we had to create a collection of this. We've not had to store it in memory. All that gets stored in memory is the running totals in the operators, and then we output the current values. So it's actually very, very memory non-intensive for dealing with infinite data. Are you impressed yet? I suspect people will say, I'm going to think about it. Just don't take deep thought type time about it. It would be a good idea to think about it for 5 minutes and then, yes, I want to do Dataflow. If you are doing data analysis. If you're not doing data analysis, then you probably don't care. So what we've got down here is just a sort of final parting shot for this bit of code. In CSP and Dataflow and so on, what's the general way of closing a channel? In the previous example, I used double.nan as the way of indicating it. Well, there is a general way, an out-of-band way. You don't send a value down it, you send the special channel operation poison. I don't know why they called it poison. It's sort of, well, anyway, you call it, you poison the channel, and that says, when all the current elements are used up, then we go. So we have poison pills. And here I am making sure that all the operators terminate. You know, if this is truly infinite, we never get here. But if we finish the stream, we need to close things down. So we're going to make sure all the operators close, and then we go away, as it were. Right. The poison has been provided. This has been read for the last 4 minutes, which means that what we actually have to do is a quick summary, which is that Dataflow is an architecture. It's a sort of approach to structuring your code. It's a way of doing some forms of concurrency, not all forms, but some specific forms. And you get the parallelism from the infrastructure for free if you set yourself up correctly. So it's a way of harnessing a particular form. GPars is really cool. At the moment, because Groovy is Java 7, it's aimed at Java 7, and I'm in the middle of ripping out all the rubbish that's not needed when we move to Java 8. But it will have to be a new version of GPars. So we're going to call it GPars 2 eventually, when it's ready. I didn't show the tests, but there's a whole new talk in Groovy testing with Spock. Excellent. Jez likes Groovy testing with Spock. And you can test your Java code with Spock, and it's really cool and makes JUnit and TestNG look sick and anemic. So you really do need GPars. I have gutted your ability to ask questions. Apologies for that. But I will be around for the rest of the day if you want to come and heckle or otherwise. Just bribery's good. And thank you very much.